Stanford University.
I gather you people had a lot of fun with entanglement. It's a good subject. I mean, it really is absolutely the heart of quantum mechanics. But of course, yeah, I mean, I would say up till now, we have really studied the foundations of quantum mechanics in very, very simple systems. And the foundations have been laid out, they've been exposed, you know what they are. And really the only thing left to do now is to study some examples.
Can I ask one question?
Yeah.
So in classical mechanics, we started with a very small number of empirical observations by Newton, and sort of everything else was obtained by mathematics, sort of more or less.
More or less.
So what's the equivalent in the case of quantum mechanics? What are the sort of basic atomic empirical observations?
You mean historically?
Well, the minimal set that you need.
Well, I would say the minimum set is what we described when we talked about an apparatus which you could rotate, a spin, and a window in the apparatus that was 0 and 1. That's logically the simplest thing you can do. It's of course not the way quantum mechanics was discovered. But just as analyzing the experimental data that you would get by taking an electron or spin, orienting your detector, pressing the M button, the measure button, and getting a 1 or -1 on the screen, doing this over and over and over again, accumulating statistics, is the simplest thing you can do.
You have to do that for each physical property, like momentum, like spin, and so on.
Yes. Right.
So a quick question on the system you described with the singlet and the triplet and the photon going off. You said if you capture the photon quickly and reflect it back. Is that simply because you only have a system with just the singlet and the triplet? Or can any other photon also cause disentanglement?
No, that's a good question. Well, no. You don't have a photon out there. You have a photon or you don't have a photon. The radiation field itself is not in a state of positive, whether or not you have a photon out there could also be thought of as a 0 or a 1. The radiation state itself, the radiation system itself, could be modeled by having another degree of freedom, and the other degree of freedom could also have a 0 or 1. 0 would mean no photon present, 1 would mean a photon present. Okay? So what happens, let's suppose we start with a singlet and the triplet superposed in this way with no photons. All right, so to express the fact that there are no photons, we have to put another degree of freedom in here, and we have to say this is a tensor product with a state of the radiation field which has no photons. That's the way, and keep in mind, this here represents the 2 electrons, either in the singlet state or the triplet state, and this represents the state of the radiation field. Now, if you wait for a little while, and while the electrons are entangled here, they are not entangled with the radiation field. This is a simple product of a vacuum of photons, no photons, and a particular state of the electron pair. In fact, I said this was entangled. This is not entangled. This combination was just up-down. All right, now you let it evolve for a while. What happens is the singlet stays the singlet, and it does not emit a photon. But the triplet, what happens to it? It becomes the singlet and emits a photon. So what happens to this state It evolves into the linear combination of singlet times no photon and one photon. In other words, it's a singlet electron, it's a singlet state of the electron pair, but a linear superposition, quantum linear superposition of no photon and one photon. That seems a little bit strange, but it's an important idea that you can not only superpose states of a particle, you can superpose the number of particles. No particle and one particle can be quantum. Any two states can be superposed. So the state of a system of the vacuum, empty space, that's a state with no photons. The state with one photon is a state with one photon, and you can add them. That's what's happening here. You would eventually come to the state which is singlet times no photon plus one photon. This state now, is it entangled between are the electrons entangled with the radiation field? No, because it's pure product. But are the electrons entangled with each other? Yeah, because it's a singlet state. Only the singlet state appears here, and the singlet state is an entangled state. So the electrons are entangled with each other, but they're not entangled with the radiation field. On the other hand, the radiation field is left in a superposition of states of having a photon and not having a photon. So what do we start with? We started with a unentangled state of the electrons, totally unentangled with the radiation field. I say this is unentangled with the electrons because that's what we started with, UD, and no photon. So we started with unentangled, completely everything unentangled, waited for a photon to be emitted. When the photon was emitted, the triplet state became the singlet state, but it emitted a photon, and the result was an entangled state of the electrons, but unentangled with the radiation field. Okay. It's a pretty tricky set of ideas.
You haven't brought anything external in, like a magnetic field, so that what's causing...
No. In order to... no, there's nothing external here.
So what causes the triplet to emit the photon is the interaction with the other electron, which is why they emit the tank.
Right. Right, the interaction between the two electrons. Roughly speaking, each electron is in the magnetic field of another electron, but what they want to do is maximally anti-align, or better yet, they want to minimize or make maximally negative the value of sigma dot tau. So they emit a photon to do that. All right, the last time we started to move on to the problem of particle motion. Forget particle spin. Of course, real particles may have both position and spin. But let's concentrate for today on questions relating to the position of particles. The simplest example we can think of is a particle moving on a one-dimensional axis, x. There it is. Before we study that, I wanted to do a little mathematical interlude. It'll take at most 10 minutes, maybe less, having to do with Fourier analysis, Fourier transforms, and its relationship to the Dirac delta function. So let's take a blackboard and do some mathematics on it. Okay. The function e to the I px, let's take p to be a number. P is a number now, it's not a variable. E to the I px. That's a combination of sine and cosine functions, and therefore it has a wave-like character, and we call it a plane wave. We call it a plane wave. just simple waves, cosines and sines. There's a combination of cosine p dot x and sine I sine p dot x. And you can think of it as a wave. Of course, it's not moving. Just writing e to the ipx doesn't give it any time dependence, so it doesn't move, but it's wave-like. Okay. A very wide class of functions, and certainly all the functions we will be interested in, can be written as sums of plane waves, or integrals, better yet, integrals of plane waves. And decomposing a function, in this case a function of x, let's call it psi of x, decomposing it into plane waves is called Fourier analysis. Now, most of you know that. In fact, most of you, or some of you in any case, know about Fourier analysis, but we're going to spell it out now. Every function that we will be interested in fact, it's probably true that that excludes almost all functions. But we also exclude almost all functions when we say that they're continuous, when we say that they're differentiable, when we say that we can express them in any meaningful, sensible form. We exclude almost all functions. But if we take our functions to be reasonably continuous, and I won't try to be very, very precise, continuous and not to blow up at infinity, in other words, to fall to zero at minus infinity, at plus infinity, almost all functions, or all functions we will be interested in, can be expanded in waves in this way. Now, expanded means they can be written as integrals over p. What is p? P tells you how fast the wave oscillates. This is some moderate value of p. If I increase p, I create a wave with a very short wavelength. Decrease p, I'm talking about a wave with a very long wavelength. So this is just saying we can decompose a function into waves of different wavelengths. Each wavelength has an amplitude, an amount of that wave that's in there, and we'll call that psi twiddle of p times e to the ipx. Psi twiddle of p is just the amplitude that the wave of type p has strength psi of p in the function psi of x. Okay? Fourier's theorem is a theorem which tells you how to reconstruct psi twiddle of p. And I'm going to, just for definition, this is purely for definition, I'm going to put a 1 over square root of 2 pi here. That's a convention. We could have absorbed it into psi twiddle of p.
Psi twiddle is complex?
Psi twiddle typically is complex, and so will psi of x be complex. That's a good question. Both of them I intend for the moment to be complex. Now, it may happen that one of these is real and the other one is complex. That can happen, but at the moment we're just interested in arbitrary complex functions. That's right. All right, the question is, how do you reconstruct psi twiddle of p from psi of x? And I'm going to leave it as something you can look up if you don't know it. It's the basic theorem of Fourier analysis that psi twiddle of p, and notice that psi of x is an integral over p. Psi twiddle of p is going to be an integral over x, dx over square root of 2 pi, times psi of x, and the natural thing would be to write here e to the ipx, but it's not, it's e to the minus ipx. Two pi, thank you. That's the basic theorem of Fourier analysis, that if psi of x is the Fourier transform of psi twiddle of p, defined in this way, then psi twiddle of p is a Fourier transform of psi of x, Very much the same pattern, except that you put an e to the minus I px there. We will need that theorem. So if you don't know that theorem, it's a very important theorem in quantum mechanics. And it expresses a kind of reciprocal relationship between x and p, which of course ultimately are going to be position and momentum. Okay, that's one little mathematical interlude that we will need. The other has to do with the delta function, and then we're going to combine them together. For a mathematician, the definition, we have a intuitive definition of a delta function. It's a high, narrow function that's so narrow that its width is essentially 0, and so high that the area under it is 1. Okay? We can call that a representation of the delta function. A definition of the delta function. Of course, the delta function is not a real function. It's infinite somewheres, but you know, that's an anal attitude about the delta function. It took years for physicists, incidentally, to convince mathematicians that delta functions were okay. Mathematicians didn't like them for a very good reason. They're functions. You can't square them, though. If you square them, they're still 0 everywhere except at the same point. But instead of having a height big enough to make the area 1, they have a height which is the square of that. And so they themselves are are worse objects. But they got over it. I mean, they got over it, and I'm told now by some of my mathematician friends that it's okay to write a delta function. Okay, properties of a delta function. The first thing, and the way a mathematician would think about it, is it's an operation that you can do on a function. In particular, you can integrate any function of x, any reasonable function of x, with a delta function, delta of x minus x prime. Oh, no, let's go a step, no, let's even go, let's not even do that yet. Let's take delta of x minus x prime times f of x. First property of the delta function is that this is equal to f of x prime times delta of x minus x prime. Why would that be true? That certainly wouldn't be true for a general function delta. The reason it's true is because delta is only non-zero when x is equal to x prime. So it's no big deal. Delta of x minus x prime is only non-zero when x equals x prime, and therefore it doesn't matter whether you put x or x prime when multiplying it by a function. So that's property number 1. Now, property number 2 that pretty much follows from that, no, not yet. Property 1, next property 2. Integral of delta of x minus x prime is always equal to 1. That's just a statement that the area under this bump is equal to 1, and it doesn't matter where you put it. You put it over here, or you put it over here, or you put it over here. The area is always equal to 1. And so the integral of delta of x minus x prime, let's say from minus infinity to infinity, is always equal to 1. And the last property, which follows from these two, is that the integral of delta of x minus x prime, f of x, is equal to f of x prime. Now, you see it in two ways. One is that you can say, look, the delta function is only non-zero when x is equal to x prime, and so it picks out the value x prime in f of x. Or you can just say, use property, where is it, property number 1, to rewrite this in the form f of x prime integral delta of x minus x prime dx. Why am I allowed to bring the f of x prime on the outside? Because it doesn't depend on x. It's just,
X prime itself is a constant value. X prime itself is a constant, is a fixed value.
from the point of view of, yeah, that's right. That's right. So I just bring it on the outside, and then I say the integral under the delta function is 1, and so I just get f of x prime. All right, so those are the obvious properties of the delta function, which you might use to axiomatize what a delta function is. Okay, now I'm going to prove a theorem which provides a representation of the delta function, an important representation of the delta function. I think we can erase this for the moment. Did I want to erase that? I probably didn't. Integral f of x delta of x minus x prime is equal to f of x prime. Now, this actually is a sufficient definition of the delta function. This is the way the mathematicians define it, as an operation that you do on a function that gives the value of the function at some point. Right? And this is enough to define the delta function. If it's not enough to define the delta function if there's only one function f. If this is true for every function f, there's only one function, only one delta here that will fill that property. Okay, so this can be taken as the defining function. If for all f this is true, then this is the delta function. What's that? Yeah, dx. dx. Good. dx. Okay, now what I want to do is I want to take the two top equations and put them together. Here's what I'm going to do. I'm going to write that psi of x is equal to this thing, but then I'm going to plug in for this thing the second equation and re-express psi of x back in terms of the function psi of x itself. And let's see what we get. Either we'll get something completely trivially stupid, or we will learn something, and the fact is we will learn something. So let's take psi of x and write it. Psi of x is equal, I'm just going to write down, integral dp over square root of 2 pi e to the I px, and now I'm going to shove in the second equation for psi twiddle of p, and that is, let's put a bracket around it, dx integral, yeah, hold on a second. Let's call it psi of x prime. And to make it psi of x prime, all we have to do is put a prime here. I've just changed the name of the variable on the left side. And to do so, of course, I have to change the name of the variable on the right-hand side. All right? I don't want to confuse x and x prime. All right, now the second equation for psi twiddle of p, that I can leave as it is, and just write that it's integral dx over square root of 2 pi psi of x e to the minus I px. So I've just plugged in psi twiddle of p. Now, integrals are generally insensitive to which order you do the integrals, particularly if they're integrations from minus infinity to infinity, as they are here, both of them. If they're well-defined and they converge and everything, then it doesn't matter which order you do the integrations. So let's isolate some things. Let's put here integral dp over 2 pi. Oh, over 2 pi. We now have a single factor of 2 pi, one coming from here, one coming from here. Let's isolate e to the I p x prime minus x from here. We have e to the I px prime, e to the minus I px, that's e to the I p x minus x prime. And then we still haven't written down psi of x, so let's write down psi of x. And now interchange the order of integration of x and p and write this as integral dx. Integral dx. That's equal to psi of x prime. So look what we have. We have a relationship between psi of x and psi of x prime. We have a way of writing psi of x prime in terms of psi of x. But what is it? But look what stands here. Take this whole thing here. This is an integral over p, it's true, but all it is some function of x prime minus x, right? Let's give it a name. Let's call it the capital delta function. Let's call this the capital delta function and write this dx capital delta of x prime minus x. This whole mess here, including the 2 pi and everything else, after integration over p times psi of x equals psi of x prime. What does it tell you about this capital delta function? It's just a good old delta function. It's just a good old Dirac delta function. So we've proved an interesting relationship, and one that is at the heart of many, many things in quantum mechanics. Here it is, the integral dp over 2 pi e to the I p of x minus x prime is equal to delta of x minus x prime. In other words, a kind of screwball way of writing the delta function, by itself expressing it as a Fourier transform or a sum of plane waves. We can also write this in another, we're not writing the same thing, I'm writing a different thing, but just by interchanging x and p, I can write another equation, dx over 2 pi e to the I x of p minus p prime equals delta of p minus p prime. These two are identical. These two are identical. I've just changed the name of x to p and p to x. Right? If this equation is true, this equation is true because they're exactly the same equation, except that I've interchanged the name x with p and p with x. All right, so this is an important, as I said, fact about delta functions. These are the basic mathematical facts that we need. This here is not important. We've got it on the blackboard over there. Oh, if you don't like the way I got the second one from the first one by just interchanging p and x, you can go back to these equations, and instead of eliminating psi twiddle of p, eliminate psi of x by substituting in psi of x from here, and you'll get, you just interchange p and x. Good. All right, so now we have what we need. Yeah.
On the left-hand side, underneath the board that you just brought down,
Yeah.
you wrote x prime minus x, but then on the right board you wrote x minus x prime. Does that imply a factor?
Actually, it doesn't matter. It's a good question. It doesn't matter, and the reason is delta of x minus x prime is unchanged if you interchange x and x prime. It's a symmetric function of its argument. If you interchange, delta of x minus x prime is the same as delta of x prime minus x. So you can check that. So the answer is it doesn't matter. But you're probably right. Probably if I did the derivation systematically, I might have gotten x prime minus x here, but then in the end, it doesn't matter. Okay, so let's add this equation over here. Integral dp over 2 pi e to the I p, either x minus x prime or x prime minus x, doesn't matter, is equal to delta of x minus x prime, and integral dx over 2 pi e to the I p minus p prime times x is equal to delta of p minus p prime. All right, now let's come back to the world of physics, the world of quantum mechanics, a particle on a line. If we were doing classical physics, we would describe the particle on the line, the state of a particle on the line, by a point in phase space. And phase space consists of a value of x and a value of p. One of each. For a one-dimensional particle, just one. One x and one p. What about quantum mechanics? How do we describe the state of a quantum mechanical particle? Well, you can try to make some guesses. Not how do you describe the state, but how do we describe an orthonormal basis of states? That always is the question. When you start a new system, you ask what defines the space of states, and one way of defining the space of states is to provide an orthogonal normalized basis of states. And all states then are linear superpositions of that basis. All right, there are various possibilities. You might wonder maybe the states can be represented by the position of a particle, x. You might think maybe they can be represented by the momentum of a particle. Or you might wonder, might the states be represented as a pair, an x and a p? This is large. After all, in classical physics, it takes an x and a p to describe the position of the state of a particle. What is it in quantum mechanics? And the answer is in quantum mechanics that x and p are too much information. In the same way that for the spin, knowing sigma x and sigma y, or sigma z and sigma y, or whatever, is too much information. You can't know both of them simultaneously. The same, of course, is true in quantum mechanics. It's actually more familiar. It's called, of course, the Heisenberg uncertainty principle, but you can't know both. So it's one or the other. Classical physics, a particle has an x and a p. In some sense, in quantum mechanics, a particle has an x or a p. Meaning to say, you don't try to describe it by both, you describe it by one or the other, and we'll see what the relationship is in a moment. So we suppose that there is an eigenvector of an observable position for every value of the observable position. This vector represents a state in which the position of the particle is definite and at position x. So it's an eigenvector of something which we'll think of as an observable x. We'll understand a little more mathematically in a moment. And like any good basis, the point of a basis is to write any wave function psi, or any state vector, as a superposition, a sum of the basis vectors. Since the basis vectors form a continuous range of possibilities, we write it as an integral dx, replacing the sum, and then eigenvector x times something which depends on x. This is completely analogous to what we've done in the past, where we've taken an arbitrary vector and expanded it in terms of eigenvectors of something. And these are the coefficients here, and we call these things the wave function. We call these things the wave function. And in fact, they are given by the inner product of the eigenvector psi, eigenvector x with the state psi, that is psi of x. This is fully analogous to what we studied in simpler systems. Wave function is the projection of the state onto a state of definite x, that's psi of x, and secondly, psi star of x times psi of x is the probability that the particle be found at position x. Now, strictly speaking, we talked about it last time, strictly speaking, you have to think of it as a particle, as a probability density, a probability per unit x, or probability per unit interval in x, but you know how to take that into account. All right, so that's, this is the basic framework of quantum mechanics just being repeated except for a continuous variable. The inner product between two vectors, x and x prime, is 0 unless x equals x prime. And if these were continuous, if these were standard discrete variables, we would say 0 unless x equals x prime, 1 if x equals x prime. We would write Kronecker delta x prime. But that's not helpful for continuous variables. For continuous variables, we write the delta function. The delta function, the Dirac delta function. It's the continuum analog of the Kronecker delta. We have bra vectors and ket vectors. If a ket vector is described by a psi of x, a bra vector, of course, would be described in a similar way in terms of psi star of x. So, kets, psi of x, wave functions, bras, psi star of x. Usual thing, nothing new here. Finally, the inner product, not finally, but the inner product, not between x and x prime, but between two arbitrary states, let's call them psi and phi, each one of which can be expanded by use of a wave function. Phi is described by a wave function phi of x. The bra vector psi, can you tell the difference between my psis and my phis when I say it? Yeah, okay. This is Greek phi, this is Greek psi. But I never say psi, I say psi. I think the Greeks do also. Anybody know?
So is this really just a bunch of sci-fi?
Somebody must have thought of that.
Write that down. Keep that. Good. Okay, and this one is described by psi star of x. And if you expand them both appropriately in eigenvectors of x, bra vectors, and ket vectors, and then use the inner product rule here for the eigenvectors of x, you will get, of course, that the inner product is the integral dx. It follows by simply expanding psi, expanding phi, and using this inner product here, but it's also hardly surprising. It's the same kind of formula that we would have previously for discrete systems. And last, but
Question. So position and momentum is too much information. So we're asserting really that it's just the position that gives us a complete basis, and pretty much anything else is going to be too much information, not just momentum.
Redundant.
yeah, pretty much anything else. Now, the only reason I'm hesitating is because we could imagine a particle moving in 2 dimensions, right? In that case, it's not clear yet whether we can know the x coordinate of the position and the y coordinate of momentum, for example. And the answer is you can. So, but if our system was just a particle in one dimension, that's it. X, and right. So that's a good point.
So does that mean that momentum then can essentially be expanded, can be treated as a psi?
Say it again.
So that essentially that means that momentum can be treated as a psi and hence be expanded by an integral involving x. Is that right?
Yes. That's what Fourier transforms are for. Right. Okay. Let's oh, one last thing. The probability density is psi star psi, not psi star phi, psi star psi. And if I integrate psi star psi with respect to x, that would be the inner product of psi with itself. And that should be equal to 1 on the basis that the total probability should be 1. In other words, nothing new again, physical states should be normalized. Normalized so that integral psi star psi is equal to 1. Okay, now, next, last time we talked about some observables, the position and the momentum. So let's review a little bit about that. Let's invent an operator. Now, capital X here, maybe I should, how can I indicate that it's a capital X? Let's put an extra line in. That makes it a capital X and therefore an operator as opposed to just a number, an eigenvalue. This is the operator or the observable whose eigenvalues are the positions of the particles, the observables. Okay, the observable values. Let's talk about the action of x when it hits a vector. That's what operators do. They hit vectors and they make new vectors. All right. I'm going to tell you what the action is by telling you how it behaves in terms of wave functions. Instead of telling you how psi acts on an abstract vector, I'm going to tell you what happens when the operator x hits a wave function. Wave functions and state vectors can be thought of as one being a representation of the other. When x hits psi of x, what it does is just multiply psi of x by x. In other words, it gives you another function. That's the nature of operators. They act on functions to give other functions. They act on vectors to give other vectors. If functions are representations or constructions which represent those vectors, then whatever linear operators are, they should be such that they do something to the wave function. And this is what x does to the wave function. It simply multiplies it by x. It gives you a new function, which it's not the same function, it's a different function, but that's the nature of it. Now let's prove something. Let's prove that the eigenvectors and the eigenvalues of this operator are what we expect them to be. You, of course, do expect them to be something. You may not realize at this moment that you expect them to be something, but as soon as I show you what they are, you will say, oh, yes, we expected that. Okay, so what is likely to be the eigenvector of capital X? Well, it should be a state. It should be a state where the particle is localized at position x. Right? In particular, let's talk about the particle being localized at point x naught. What would we expect the eigenvector to be? It should be a function which is 0 everywhere except at x naught, right? That's what we would expect. It should be concentrated at x naught. And so let's try the function delta of x minus x naught. X naught is just a parameter here now. It's a function of x, but it's the function of x which represents the particle at position x naught. And let's ask the question, when you operate with the operator x on this wave function, what do you get? Well, the answer is you just multiply it by little x. But now we go back to one of the properties of the delta function, namely that when you multiply it by any function of x, you can replace it by a function of x prime. So, or in this case, x naught. This is also equal to x naught times delta of x minus x naught. But what is this equation? This is exactly the equation for an eigenvector of the and eigenvalue of the operator x. The operator x hits the wave function and gives a number times the same wave function. Okay? Operator hits wave function, gives number times wave function. It's clear that this is an eigenvector of the operator with eigenvalue x naught. All right, so now we can make a list of eigenvectors of various observables. We're starting our list, eigenvalues and eigenvectors. The eigenvector associated with a particle localized at point x naught, that is equal to the delta function of x minus x naught, exactly as you expected, right? Good. Okay. I'm sure you did. And that finishes up x. What about p? What about momentum? Again, momentum being an observable, you can observe it. If it hits you in the side of the head, you feel it. You recoil. That is what momentum is. It's, momentum means the same thing in quantum mechanics as it does in classical mechanics. It's conserved. And so if you absorb something with some momentum, you recoil. All right, what is the momentum operator? The momentum operator, and the justification for this will come a little later. We did talk about it, but I want to go back over it. Momentum is called P. The operator momentum. The operator momentum is equal to, there's no point beating around the bush, let's say what it's equal to. It is equal to minus I, and I'm going to put in some units here. Later on, we will set h bar equal to 1. It's just a choice of units, but for the moment, let's keep h bar there, times the derivative operator, d. The thing I called d last time, or the operator d. Last time we studied whether capital D was Hermitian or not, and we found that it was not. But if we multiplied it by I, either with a plus or minus sign, it doesn't matter. If we multiply it by an I, then it becomes Hermitian. So we worked that out last time. If you remember that little trick with the integration by parts, we found that D was not Hermitian, but I times D is. All right, so this is the definition of the momentum operator. Or it's a bunch of symbols so far. But what does P do when it acts on a wave function? It just gives minus I h bar times d psi by dx. So it is also an operator. It's also an operation. It's an operator, it's a linear operator, and it is a Hermitian linear operator, P. So that's what it takes to qualify as an observable in quantum mechanics. At this point, since psi is only a function of one variable, it doesn't matter whether I use partial derivatives or just ordinary derivatives. Let's call them ordinary derivatives, d psi by dx. Next question, what is the eigenvectors of the momentum? The eigenvectors of the momentum satisfy P on psi, or minus I h bar, d psi by dx equal some eigenvalue, some observable value or some possible outcome of an experiment, let's call it P naught, times psi. And this, of course, P naught is a number. It's the eigenvalue. We can, let's just, if we get rid of the minus I here, it becomes a plus I on this side, and we can divide by h bar. All right, so this is just the equation for an exponential derivative being proportional to the same function, and the solution for psi. It's unique apart from a multiplicative constant, psi. This is the eigenvector as a function of x. And let's label it by P naught, all right? Just to label the fact that it's the eigenvector for momentum P naught. It's a function of x, and what is it? It's e to the I P naught x. Question?
Over h bar.
Oh, thank you. Over h bar. All right, I'm just going to keep the h bar around for about 10 more seconds. I just want to point out that this is a wave-like thing. This is a wave-like thing. It has sines and cosines, and it has a wavelength. The wavelength is the distance that you have to move so that the thing in the exponent changes by 2 pi. In other words, if we call the wavelength lambda, P naught over h bar times lambda equals 2 pi. That's the definition of the wavelength. How far do you have to move so that the sines and cosines return to themselves, or that the wavelength is 2 pi h bar divided by P naught. P naught being the momentum of the particle. So here we see the first example of the relationship between momentum and wavelength. Larger the momentum, the smaller the wavelength. Of course, we have not yet justified the choice of the terminology momentum for this thing. But we can keep in mind that later on we're going to want to come back and see that this P really does behave like momentum. But so far it's just an abstract observable. We don't know what it means yet. Okay, so here we are. Lambda is equal to this. And now that I have demonstrated that, let's get rid of h bar because I will forget about it anyway. Let's get rid of h bar, get rid of this formula here, and say this is the... Now, it's not clear yet that I've normalized this correctly. It's not clear yet that this is normalized to 1. Let's take the inner product between two momentum states. All right, this here is a representation of the momentum state P naught. Or let's just call it P. Let's just call it P. Get rid of the naught. It's not serving any real purpose here. P. But think of P, just P. Let's take the inner product of two momentum states, P prime and P. Where's our formula for inner products? Here it is, right over here. No, here it is, over here. One psi star and one phi. So that means the inner product is the integral of e to the minus I p prime x, that's the wave function of p prime, or the complex conjugate of it, and then the wave function for e to the I px dx. Or equivalently, integral e to the I p minus p prime x dx. Now, if we've done things right, since P is supposed to be a observable, a Hermitian operator, and the eigenvectors of Hermitian operators should be orthogonal, then this should be 0 if p is not equal to p prime. It's pretty clear that it is 0 if p is not equal to p prime, and for the following reason. The real and imaginary parts of e to the I p minus p prime x are cosines and sines. If p is not equal to p prime, these are cosines and sines of p minus p prime x. Cosines and sines are as positive as they are negative. If you integrate them over a large interval, you'll get 0, as long as you pick up an integer number of wavelengths, and that's important here. So as long as p is not equal to p prime, this integral just oscillates itself to 0. Okay? Equally positive and equally negative for both the real and imaginary parts. So it is true, p prime is not equal to, the inner product is equal to 0 if p is not equal to p prime. What about if p is equal to p prime? This is integral from minus infinity to infinity. Without looking at the other blackboard, what can we say about this for p equal to p prime? It's going to be infinite, right? The integral of 1 integrated over all space is infinite. So in fact, it's sort of it's smelling like it is the delta function. It's smelling like it is the delta function, infinite when p is equal to p prime, and 0 otherwise. It's a good thing. But we don't know what the actual numerical coefficient is. But yes, we do. Up here we have integral, where is, that's this one over here. Integral dx over 2 pi is delta of p minus p prime. The upshot of this is just that in order for this to be normalized, so its inner product is a real delta function, you have to divide by the square root of 2 pi. Yeah, square root of 2 pi. Big deal. Square root of 2 pi. This is the wave function for a particle of momentum, 2 pi here, a particle of momentum p. We now know what the wave functions of particles of momentum p are.
Question?
Yeah.
When you were talking about two different p and p prime, you talked about taking the integral from minus infinity to infinity of some oscillating function,
Yeah.
and you said this is 0. And I'm just trying to think in my head, normally when you do an integral, how do you justify that as 0? Yeah, I can see it's sort of average 0, but I'm not really sure how to justify it.
Yeah, I knew somebody was going to ask. Yeah. The answer is that you really justify it by starting with a theory on a finite interval. You're asking, I think, questions about convergence of the integral.
Right.
Integral doesn't really converge. So you really have to go back to some earlier starting point, which if I were teaching quantum mechanics in a graduate class or something, I would have started by thinking of a theory on a finite interval, or even better, on a finite periodic interval, worked it out, and then taken carefully the limit as you let things go to infinity. And then everything could be justified with rigor. We don't have the time, and so I don't do that. But of course,
About the Fourier transform itself, right? Because
yeah.
it's not really quantum mechanics, because I was just thinking about the...
It's a fact about the Fourier transform, but I did cheat. At some point, I interchanged an x integration with a p integration, and one of those integrations didn't converge. I did basically the same cheat that I did here. But you know, I wouldn't cheat you if I didn't know that the steps can be filled in, and if I didn't know that if you go and find yourself a book on Fourier transforms, you won't be able to fill the steps in yourself. So I haven't really cheated. What I've done was just a little bit of a shortcut. All right, now we've talked about the wave functions of particles with momentum p, but now I want to talk about a different concept, the wave function in the momentum basis. So far, all of these wave functions have been thought of as functions of x. P here is just a parameter. It's the momentum of the particle, but the wave function is a function of x. Oh, incidentally, notice something important. Notice something important. The wave functions of particles with definite momentum oscillate endlessly forever and ever, and they're absolutely unlocalized. They're as delocalized as they can be. In particular, psi star psi of x is uniformly spread out over the entire real axis. In no sense is the position well defined. It's as uncertain as it could be. On the other hand, the momentum is very precise. This is an eigenvector of the momentum operator. If this were the wave function of a particle and you measured its momentum, it would be p. If you measured its position, it would be random all over the axis. Okay? Very much, well, much worse than, but very much like the sigma x and the sigma z representations, where one may be definite and at the cost of the other one being as indefinite as possible. In that case, it's just 1 and minus 1. Here, it's much worse. So when a particle is localized in momentum, it's completely delocalized in position. We want to be able to say, I would like to do the reciprocal thing also. I'd like to go in the other direction. For that, what we want to do is construct a notion called the momentum space wave function. The momentum space wave function is related to the probability amplitude for finding different momenta. So let's see if we can construct that. For that, I think we're finished over here. Let's see. All right. We defined, in general, we define a wave function by taking the state vector and projecting it onto eigenvectors of various observables, and that gives us the wave function in the basis associated with that observable. If I project it onto an eigenstate of x, that gives me the wave function psi of x. If instead I project it onto a state of definite momentum, that gives me something that I can call the wave function in the momentum basis. Okay, it's not a function of x, so it doesn't look like a wave in space. Doesn't look like a wave in space, but it's called the wave function, and it's a function of momentum. What is it? Let's give it a name. Let's call it psi twiddle of p. Just to I use the twiddle notation just to remind you that it's a different thing, a different animal from the x wave function. How do we calculate this? Let's suppose we know the x representation of the state vector, psi of x. How do we calculate this? Well, we take the inner product of the state vector psi with the vector p. But we know what that is. That's the integral dx. I think I've lost it. No, I don't mean, yeah, only the equation. What was it? Psi phi equals integral psi star of x phi of x dx. Okay, so I want the inner product between p. Well, I know the wave function of p in the position basis. It's just, what is it? It's e to the minus I px over the square root of 2 pi, if I remember, right? That's what we wrote down for psi sub p of x. That's this guy over here. And then we have to multiply that by psi of x and integrate. But that's exactly equal to psi twiddle of p with the same notation that I used for Fourier transforms. In other words, the momentum state wave function, psi twiddle of p, is exactly the Fourier transform of the position space wave function. That's the upshot. Momentum and position are related in the same way that ordinary variables, positions, and Fourier variables are related. Okay, so here we have, let's just call it psi twiddle of p. And if you know, what this says is, if you know the wave function and the position basis, you know everything. That's enough. In fact, you can recover the wave function in the momentum basis, and also the probability to find the particle with different momenta. After all, what is I've abused the notation. This shouldn't be a capital psi here. This should be a small psi. It's a wave function. And of course, the probability to measure a given value of momentum is just psi twiddle star of p times psi twiddle of p. So, what do? In some way or another, you know what the wave function of a particle is, psi of x. But you're not interested in measuring x. You're interested in measuring p. How do you determine the various probabilities for measuring different p? You take that x wave function, you subject it to Fourier transform, you find the Fourier transform of it, and its square is the probability for different momentum. This is extremely similar to going from the sigma z basis to the sigma x basis. Go through it and see if you can find the similarities between the two.
So if you wanted to take a position operator in the momentum space, it would be IH bar partial P.
Right. Remember, P was equal to minus I d by dx. And you apply this to a position space wave function. You apply it to a position space wave function to find out how it acts. X, not quite parallel, not minus I d by dp, but plus I d by dp. The minus sign difference has a great deal to do with this minus sign here, but you can work it out. Right.
This is the first time that I've seen an explanation for a Heisenberg pair of quantities, like a position versus momentum. And I assume that a similar relationship would apply to other Heisenberg pairs like time and energy.
Time and energy is a funny one. Time is not usually regarded as an operator in quantum mechanics. It's not usually regarded, although you could. You know, you do measure time. You look at your watch. The hand of your watch is an observable. And so in that sense, clock readings can be thought of as observables. There's something a little bit funny about them, and I don't want to get into it now, but usually in quantum mechanics, time is just considered the parameter by which states evolve. But it is true. If you have a clock, for example, and you're interested in making that making an extremely accurate observation of the clock, it will be at the cost of a lack of precision in the energy of the clock. So, yeah, it is.
What other Heisenberg pairs are there that I might not be aware of?
Electric and magnetic field, just almost anything you can think of will have a conjugate variable. Electric and magnetic field. What's that?
Temperature and pressure?
No, temperature and pressure are statistical mechanical variables. They're not quantum mechanical variables. What's that?
Angular momentum.
Yeah, well, okay, the angular momentum and angle. If the angular momentum in a axially symmetric system, the angular momentum and the angular orientation would be another one, yeah. Okay. And there are lots of others. Usually, for example, if you have some field, typically the field and its time derivative are conjugate variables. So there's all kinds of any other questions? Yes.
It seems like when we went from discrete states, observables with discrete states to continuous, there's a kind of subtle change in representation in the following sense that in that case, the discrete states, the operators operated on the kets. The wave function was just an expansion coefficient.
Yeah, but we could, right, but we could also, remember we also represent the operators as matrices and the kets as columns. But a column is just a list of values of an amplitude as a function of where it's lying, how high, as a function of an eigenvalue. So it really is the same thing. This is closely related to the representation of operators as matrices. Just a concrete action in a particular basis. When you write column vectors, you write them in particular basis. Right. All right, last remark about uncertainty is the uncertainty principle. For this particular example here, I'm not going to derive the uncertainty principle, not today, we may get to it, but it really is a very simple thing. It is simply the statement that it's a statement about Fourier transforms, first of all, and it transcends quantum mechanics. It's not only quantum mechanics. Anytime you have a pair of quantities which are related by Fourier transform in this way, it's generally the case that the narrower one Fourier pair, for half of the Fourier pair is, the broader the other one is. In other words, the narrower the range of P, the broader psi of x will be and vice versa. So I don't want to go into a mathematical statement about the uncertainty principle here. But whatever it is, it really just does have to do with the character of Fourier pairs, x and p in this case. We'll come back to it, I think. What I wanted to get onto was the Hamiltonians for particles. Just the simplest possible Hamiltonians for particles and how they govern the quantum mechanical evolution. Remember what the Hamiltonian is? The Hamiltonian is the thing which, first of all, enters into the Schrodinger equation and which also governs the time evolution of the state vector. The Hamiltonian is to be identified with the classical idea of energy, just as it is in classical mechanics. If you go back, I discussed this earlier, but let's go on. The starting point was the idea of the unitary evolution of state vectors, that state vectors evolve by unitary transformation. And then we said, well, what happens if you make a tiny little change in time? That should correspond to some sort of differential change in the state vector. And we found out that that differential change was governed by a Hermitian operator called the Hamiltonian. So if you have forgotten the details of that, go back to it now. Not right now, but you'll remember the equation. The equation for the evolution of a state vector is let's put our h bars in for the moment, take them out again in a little while. d psi by dt, the way the state vector. We can write this in terms of state vectors. The state vector is generally a function of time. The state changes with time. You can take the difference between vectors, and you can differentiate vectors with respect to time. If a vector happens to be time dependent, you can differentiate it. I d psi by dt is equal to the Hamiltonian operator acting on psi. That's the time-dependent Schrodinger equation. I think we worked out an example for a spin processing in a magnetic field, where we just used for the Hamiltonian one of the components of the spin. Here is the general form of the Schrodinger equation, the time-dependent Schrodinger equation. And let's try out some simple Hamiltonians, see what kind of things we learn from them. Tonight I think we'll just study one or two, and then we'll go on afterwards. The very simplest Hamiltonian that I can write down, which is quite illustrative, and nobody ever writes it down, but I'm going to write it down anyway. Is H. Now H is an operator. Not just an operator, it's a Hermitian operator. H doesn't stand for Hermitian, stands for Hamiltonian, but never mind. I'm going to try H is equal to a number, constant, C for constant, times the momentum. Perfectly good thing. Let's see what it does. Let's see what kind of thing we learn from it. Is this a reasonable Hamiltonian for a particle? Yeah, actually it is, and we'll find out in a moment what kind of particle. But it's not the usual thing. What do we usually write for a non-relativistic particle? P squared over 2m, huh? Momentum squared over twice the mass. We'll come back to that. But this is simpler. This is simpler and worth exploring first, just to see how the apparatus works. Everything here should be capitalized, everything, because they're all operators. Okay, but how is this represented in terms of wave functions? In terms of wave functions, and wave function psi of x, wave functions in the x basis, in the momentum basis. Wave functions in the x basis are just projections onto the x eigenvectors, and we can do that inside these equations here. It's fine. What this reads then is I h bar d psi of x by dt, this is the way the wave function changes, is equal, now h is c times p, so let's put the c there, and p is minus I h bar d by dx. So there's a minus, an I, an h bar, and a d by dx, psi of x. Okay, what have I done? I've rewritten this equation in terms of wave functions. In other words, a concrete representation, psi of x, d psi of x by dt. And I've used here the assumption that the Hamiltonian is just equal to c times the momentum, and the momentum is I minus I h bar d by dx. Well, this is and of course psi is not only a function of x. What is psi a function of? Time. It's a function of time because in general a state vector changes with time, that's all. Okay, we can, let's cancel out the I h bars, and I just get d psi by dt is equal to minus c times d psi by dx, or d psi by dt plus d psi by dx with a c is equal to 0. That's a pretty simple equation. In fact, it's so simple that I know not only what a solution is, I know all of the solutions of this equation. Anybody know what the solutions of this equation are? The general solution? A function of x minus ct. Any function, let's leave it this way. Any function which is a function of x minus ct, in other words, it doesn't depend on x and t separately, it only depends on the combination x minus ct, will solve this equation. If I differentiate with respect to t, that will be minus c times the derivative with respect to x, and that's all this equation says. Any function of this form will solve the Schrodinger equation. So let's think about a function of this form. What does it do? What does it look like? You can start at t equals 0, cross out t here, with any function psi of x. Of course, we don't want to take any function. I want my functions to be such that the total probability is equal to 1. So the integral of psi star psi should be finite, equal to 1. They shouldn't blow up, or they should fall to 0 nicely so that we can integrate them. But they can do whatever you like. Some sort of lump. It can oscillate, may or may not oscillate, and it's rather general. And now we let t run. We let the time go forward. What happens to this solution? What happens to the solution is it stays exactly the same shape, except every feature of it moves with a velocity c. The features of it move to the right with uniform velocity c. That's what this function is. It's just a function which just moves rigidly without changing its shape. And of course, it's a complex function, so it has a real part and an imaginary part, but both of them maintain exactly the same shape, and they just slide down the axis uniformly with a velocity c. Now, I chose c for a reason, because it's the speed of light. Is this a photon? Well, this is not really the correct description of photons, but it's pretty close to the right description of neutrinos, at least neutrinos which move with the speed of light. Real neutrinos probably move a little slower than the speed of light, but unmeasurably so. So this would be a darn good description of one-dimensional neutrinos, except that we would have to add another possibility that they can these are pure right-moving neutrinos. They're pure right-moving neutrinos, and they do have a funny thing that the energy can be, we're going to come back to this, not this quarter, I think, but the energy can be both positive and negative. P is a thing which can be positive or negative. So this particle has the property that it can have positive and negative energy, but that's not important. What's important here is the picture of the wave function moving down the axis with uniform velocity. The whole probability distribution rigidly moves down the axis. What happens to the expectation value of x? It moves the same way. So the expectation value of x moves with velocity ct. And that's the quantum mechanics of the simple system. I would just point out that if we compare this with the classical mechanics of exactly the same system, Hamiltonian is equal to Cp. How do we compare how do we do the classical physics? We use Hamilton's equations. So here, it was mainly for this reason right here that we did all quarter of classical mechanics last quarter. So that, well, not just for this one, but for all sorts of things like this. Hamilton's equations. Let's look at Hamilton's equations. Hamilton's equations are dh by dp equals x dot, and dh by dx equals minus p dot. the h by dt is just equal to c, right? The h by dx, that's equal to 0. So what this says classically is that the momentum is conserved. Now we'll come back to the conservation of momentum in quantum mechanics. But it also says that the position of the particle moves with velocity c. In quantum mechanics, the whole probability distribution in this case, this is a very, very simple case, sort of engineered just to have a simple answer. The whole probability distribution moves with, but in particular, the expectation value of x moves with velocity c. So the expectation value of the position behaves according to the classical equations of motion. Now, that's this, as I said, this is a very easy example, which is a little too simple to be perfectly general, but it does illustrate the. So this would be the Schrodinger equation for this very, very simple Hamiltonian. Okay. I think we're about. All right, let's go a little more. What about and of course this would make this a relativistic particle. This would not be a non-relativistic particle. This is a guy who moves with the speed of light. Okay. Oh. Yeah.
I mean, without using the c, just using some other number so it's not the speed of light, would this be the correct Hamiltonian for any particle moving in free space?
No, any particle which is always constrained to move with the same velocity.
Right.
So, right. So, for example, just as photons are the quanta of the electromagnetic field, sound waves in crystals also have quanta, and those sound waves are called phonons. And at least at low energies, those phonons move with a uniform velocity, the uniform velocity being the speed of sound. So if you had one-dimensional phonons, you would describe them in a similar way.
But couldn't you just do that? Would you just throw an electron in free space and it wouldn't follow that?
No, electrons don't generally move with the speed of light.
No, I'm just saying at any speed.
Or no. You see, this law of physics for this particular kind of particle says that no matter how you throw it, with whatever momentum you throw it with, it's always going to move the same way. Right.
He said replace the c with the v.
With a what?
He said replace the c with velocity v.
But velocity v means momentum.
But PV is the same as p squared over 2m.
Not quite. It's it's p squared over m, but that's close to right. That's close. Right.
Imagining that if any particle.
Of course, one thing. For a relativistic particle, of course, p is not v over m, but you're on the right track. Yeah.
I was just imagining that any particle has a wave function for its position, right? And if it's moving in space, that wave function is just moving.
No. You see, that's not quite right. Only for this very, very simple situation does the wave function move with this rigid behavior and maintain its shape. Not true more generally. If you take a non-relativistic electron, we're going to work out its equation in 2 minutes. The shape of its wave function is not maintained. It sort of wobbles and does things and sort of gradually falls apart and disperses. Diffuses, disperses, whatever you want to call it. So, right, I picked this one just because it's easy to solve, but it doesn't represent the most general kind of motion of a particle. All right, so let's take a guess. Let's take a guess for a non-relativistic particle. I think I already earlier showed you that the equations of motion for expectation values quantum mechanically are very closely related to the corresponding equations of motion classically, Hamilton's equations, or Poisson bracket form of them. So you can imagine that if you want to represent the quantum mechanics of a system whose classical physics you know, you basically use the same Hamiltonian. Now, we will come back to that. We'll come back to that and justify it better. But the natural Hamiltonian to guess for a non-relativistic particle is just a good old p squared over 2m. This is not a particle with a force on it. This is a particle with no force on it, a free particle. The energy, the kinetic energy T, is equal to 1/2 mass times velocity squared. Momentum is m times v. And we can rewrite the kinetic energy, if that's all there is, let's call it h, as p squared over 2m. So that's the Hamiltonian for a classical particle. Notice this Hamiltonian has a funny feature. Particles can only move to the right. There is no left-moving motion. They all only move to the right. And that's a funny thing. The asymmetry between left and right has to do with the fact that p goes to minus p when you invert left and right. The Hamiltonian changes sign when this Hamiltonian when you that's a funny thing. The energy of a particle with negative momentum is negative. Energy of a particle with positive momentum is positive. That's a little bit weird. Okay. Ordinary non-relativistic particle, its energy is independent of which way it's moving, and that's ensured by the fact that the energy is proportional to p squared, not p. All right. So let's start with the energy being p squared over 2m and work out the Schrodinger equation for it. Now we will be working out the genuine Schrodinger, the original version of the Schrodinger equation for a free particle. All right, we just write h is equal to p squared over 2m. H is also I d by dt. Now, let's put h bar in just as Schrodinger would have done it, on psi. That's the left-hand side, thought of as an operator operating on that's I h bar d by dt. And the right-hand side of the equation is just h acting on psi, but h is p squared over 2m. So let's write that. There's a 1 over 2m. And then what is p? Whatever p is, we have to square it. But let's write down what p is first. Minus h bar I h bar, derivative with respect to x. But we have to square it. It's p squared. Squaring it just means multiplying it by itself. So let's square this, I h bar squared, and then the square of the first derivative is the second derivative. It means you just apply it twice, times psi, or on psi of x. That's it. That's the Schrodinger equation for a ordinary non-relativistic particle moving on a one-dimensional line. Let's leave the h bars. I h bar d psi by dt is equal to minus h bar squared. The minus comes from minus I squared over 2m d second psi by dx squared. This is a kind of wave equation. Incidentally, this is also a wave equation. This is a wave equation, and psi is a wave function. This is a wave equation. Psi is also a wave function. This is the Schrodinger equation for an ordinary non-relativistic particle. It has the property that waves of different wavelength move with different velocities. Well, I'm getting a little tired, so we're going to quit soon. But waves of different wavelength move with different velocities. Because of that, the wave function does not maintain its shape. And in fact, it tends to fall apart and spread. Okay? The wave function spreads out with time, unlike this very simple case over here. In this case, no matter what the wavelength, no matter what the momentum is, they all move with the same velocity. Not so here. Different momentum move with different velocities. And so a wave with a given shape, different parts of it will move with different velocity. Different wavelengths in it will move with different velocities, and it will sort of fall apart. We'll study it a little in more detail, and we'll study its behavior, but I think I'm...
For more, please visit us at stanford.edu.